All right, August 25th. So first off, does anybody have any questions at all? Nope. Okay. Well, today we've got volcanoes on the schedule, on the syllabus. And in Canvas, so we're pretty much done with week 1 stuff. If anyone is still has anything outstanding for the sedimentary rocks assignments, you can either bring them to class tomorrow or email or something like that. And if you're unable to come to lab tomorrow, same thing with the week 2 stuff. So in Canvas, under week 3 assignments, I have put a couple of links to videos, how to draw contour lines on a map and how to draw topographic profiles, because those are two exercises in your assignments. So those are there along with the pre-lab video. And I feel like I have to put something there. So for next week, chapter 1, exercises 1.1 and 1.2, and all of chapter 9. So that's due next Wednesday on the 2nd. Okay, so I thought that after volcanoes, I would also go over how to draw contour lines on a map. And I realize we haven't talked about this yet, but I'll go ahead and give you a little overview. If you are comfortable with that, or you feel like you need to wait until you've got this week's if you're comfortable with the map stuff as it is, and you can we can talk about it another time, but if you want to just get this week's stuff done and worry about it a little bit later, I understand that. We can talk about it again, but I'm definitely gonna stay on here and record how to do those map assignments. And I'll give you a little bit of maps overview. Okay, so share screen, yes. Okay, volcanoes, can everybody see that?
Yes.
Yes, thank you. So if the slides don't move for you, let me know. Hopefully we got this going. Okay, volcanoes. So we talked about igneous rocks and how they are created along with volcanoes or part of volcanoes. So you start out with magma, which again is the molten rock. Got some crystals, got some melted rock, and some dissolved gases, or volatiles as it's called. Magma that has erupted out of the ground is called lava. So the magma can behave differently in different volcanoes, and definitely does. That is determined by what temperature it is when it either erupts from the surface or is stuck in a magma chamber and starts to cool and crystallize. What is the composition of the magma? Does it have a larger amount of silicates, light colored silicates, or a larger amount of dark colored silicates? And also the amount of dissolved gases, especially water or water vapor. That's really a thing that makes the magma act differently. So all these things are part of what you call the viscosity of the magma. How well does it flow? The more viscous something is, the less it wants to flow. So honey is more viscous than water. Okay. So all that controls what an eruption will look like and act like. Syrup is more viscous than water too. So actually honey is probably a better analogy. So if your magma is hotter, it's going to flow more easily. So think Hawaii. Hawaii eruptions are fairly, very gloopy, and they flow pretty well. The Hawaii also has a lower silica content. So that means it's less viscous. It flows better. If your magma has higher silicates in it, then that's stickier, more viscous, and this would be a rhyolite or andesite, like in the Andes Mountains. So what happens is the more silicates you have, then those tetrahedra start to link together. There's more in contact with each other, and they start to crystallize, which impedes how the magma flows and erupts. Dissolved gases, so then there's a little chart down there. Water vapor reduces viscosity, so it makes it flow more easily, so it does not allow the silica tetrahedra to chain up as easily. As the magma goes to the crust, it buoys up to the crust, those gases begin to expand because the pressure is lowering. Then as it erupts, they expand even further. So however easily those gases come out of the magma will also determine how gooey or less viscous, or on the other end, how violent, how pyroclastic the eruption is. Pyroclastic is something like what happened at Pompeii. That magma was very, very viscous and had a lot of gases in it and just exploded with lots of rocks and shards and things. So total opposite of what Hawaii eruption looks like. So I'm probably going to say Hawaii a lot. Hawaii has a very fluid type of eruption, and sometimes the eruptions can last for years. Then on the other side, a pyroclastic or explosive eruption has a very, very highly viscous magma. And on the left is a fluid basaltic flow. Yeah, it's throwing magma or lava up in the air, but you can see it's red hot and it will flow a lot more easily. That's a pretty short volcano. And on the right, there's a volcano that's erupting with a lot of ash particles and expanding gases. And that's what creates that cloud that blows the material up into the atmosphere. So all that ash that's there is going to come down and rain down on the surrounding area. Okay, most lava that is erupted is going to be basaltic lava, since most lava that is produced in the ocean at the mid-ocean ridges. That's going to be basaltic lava. Then andesite's a little bit are a lot less common, and then rhyolite is even less common. On Hawaii, they've named the different kinds of flows. And that's how you say it. Flows are rough and jagged. You don't want to walk on it because it hurts your feet. And that's why they say True story. And then pahoehoe are ropey, smooth flows that are there on the right-hand side. So even though that looks crystallized and looks kind of solid, the pahoehoe, it's still very, very thin, and you don't want to step on it because your foot will go right down into the magma. So this right here, this is probably solid, and then this is moving very slowly. You can outrun this. Right? Some places have caves that were formed by lava moving through the rock, and it just moved right through and just bored right through it. Lava went somewhere else, and these are called lava tubes. There's a Lava Beds National Monument in California, and you can walk through these things. Something like on the right, these are called a skylight. So again, you don't want to step on something that maybe looks solid because it may not be and collapse. So not that you do that because they don't let people go near that. But a block lava is an eruption of literally blocks, chunks, large chunks of andesite or rhyolite. Pillow lava, and you can find all kinds of stock footage. This is lava that flows in the ocean, and it looks like toothpaste coming out of a tube. And the outside cools very quickly, which turns it into a sphere type form. So these things are billowing out like balloons and toothpaste coming out of the tube there. So you get these pillow lavas. And these can stay in the rock record. They can be buried by other sediment, and the structure will stay there. So sometime in the future, or even now, we can drill down and find these things and see that that eruption happened at some time in the past. So everything we're seeing in geology, everything that either rocks lithifying, igneous rocks, metamorphic rocks, anything like this that gets put into the crust, we can drill down a few miles in some cases and pull up a record of what happened in the past. That's important for geologic maps. That's what's used partly for geologic maps. Gases are very, very small amount. Maybe up to 6% of the weight. However, a gas can take up a small volume when it's compressed, and it expands to take up its whatever the size of the void or the room when it's expanded and under almost no pressure. So those gases escape. Most of it's going to be water, H2O. Some will be CO2, carbon dioxide. N is nitrogen. SO2 is sulfur dioxide. That's the rotten egg smell. So that's that yellow sulfur I showed you. And then there's a few others. Mostly it's going to be water and carbon dioxide. The lava fragments, the ash, rock, whatever size it might be, that's a pyroclastic eruption, and those are pyroclastic materials. It can be, and it depends on the volcano. Each volcano is kind of unique as it has its own type of magma, its own eruptions. So you get all these different sizes, and this is just to show you all these different sizes. Volcanic bomb. We have one in the lab. It's kind of neat. Looks like a football. It's heavy, and it looks like it has moved through the air and it taken the shape of a football because it was cooling as it was flying through the air. And just the different sizes of things you can see. You can have ash, and then anything up to like a size of a small car. Okay, so when lava crystallizes and cools very quickly and quenches, so these are the extrusive igneous rocks. The darker one here is called scoria. Sorry about that. So who just entered the room, please? I just see your phone number. Please tell me who you are, or I will remove you from the room.
Oh, is it? I think I'm on my phone. Is it screwing stuff up?
No, no, it's somebody just asked to enter, and it was on just a phone number. I think they're gone.
Okay.
We just don't want somebody, I don't know, coming in and.
Okay.
I don't know what. No, Trevor, I got you. It says Trevor's phone, so you're good. People have done that last semester. I'm not sure what's going on there, but okay. All right. So scoria is reddish brown, and you can see all these holes. Those are bubbles created by the expanding gases, and they're frozen there, so the structure is preserved. Pumice is also, that's weird. Pumice is a light-colored vesicular rock. Again, you can see the bubbles, structures preserved in that rock there. Sorry, I don't know where that red line came from. Anyway, okay. So a volcano will have different parts to it, different structures. A fissure volcano is a long crack in the earth, and the magma just extrudes in a long curtain. There are fissure eruptions in Iceland, and you can probably look for video of that. I usually show a video about the different types of volcanoes in Iceland, and they're all different, but we don't have, I wish we had time for that. But a conduit is basically a tube that goes up to the surface. So a fissure can also be crack deep down, and it can come up to the surface. A vent, the opening at the top, and then the cone is the structure created by the material erupting from the volcano. Sorry, I'm not answering my email right now. You can see here that material is layered because of the different eruptions that have occurred over time in here. Okay. Crater is the depression at the top where the lava comes out, fairly small, less than a kilometer. A caldera is a volcanic crater that has collapsed, usually after massive eruption. Yellowstone. The park and around it, the park surrounds the caldera. So go on Google Earth and see how large the park is, and then you can see the caldera is inside that park. It is very long in diameter. You don't realize you're in it because the caldera walls have been eroded over the last 600,000 years since it last erupted. Then you can have vents on the sides and fumaroles, which just emits gases, and that's a a spot that a volcano scientist will go stick in a temperature, a thermometer, take gas samples to try to get an idea of the composition of the magma. All right, so there are three main shapes of volcanoes. Shield volcanoes are like Hawaii. They are broad and a little bit dome-shaped, and they're very long and large. Galapagos. Mauna Loa is the largest volcano on the planet currently. Kilauea is the one that is erupting right now. So, see how long and low that is relative to others. As the Pacific plate moves, it's moving over that fissure, that crack in the crust. And it's actually, Hawaiian Islands are moving to the northwest. So all the islands to the northwest are dormant or extinct volcanoes because they've moved away from this magma source. And right now there's a new volcano forming off the east coast, or just to the southeast of Kilauea, and it's going to eventually grow so it reaches the surface and add to the island. All right, then we have cinder cones. These are pretty small, short, and they're short, small, and fairly steep. Paracutin in near Mexico City is an example of a cinder cone. Okay, so we've got cinder cones usually in large lava fields. There are some of these in Nevada. There was a very large lava eruption there, and there are many cinder cones. I couldn't tell you how many, but I do know that there is a large amount of lava there. So here's one in Arizona. As you can see, it's kind of short and round. Usually this will have a pyroclastic type of eruption. And here's Paracutin, and it erupted for 9 years, buried that whole village. It started out, there was not a volcano there. There was a field there, and a farmer was working his field and saw, the lava started to billow up, and it was created pretty quickly. Then we've got composite volcanoes. These are like Mount St. Helens. These are large and what you would think of as a volcano, your stereotypical volcano. Most of these are going to be circling the Pacific Ocean, and that's called the Ring of Fire. They're very tall and pretty symmetrical. This is Mount Kilimanjaro. It's a composite volcano. And I've got a question for you, just looking at this photo. You see all this on top of the volcano? That's how tall it is. It's got this ice on top. Right now it's dormant. What would happen if it started to erupt? Anybody have a guess? No? No guesses?
Well, when the lava would come out, it would hit the cold temperatures and it would cool very quickly.
Yeah, that's part of it. Yep, that's part of it. But I will, there's a certain type of eruption, and we're coming to it. So here's the relative sizes of the different types of volcanoes. A shield volcano, a cinder cone, very tiny, and a composite cone. Mount Rainier, Mount St. Helens. Pyroclastic flows are very, very hazardous and very dangerous. It's not just ash and lava, it's hot gases. The volatiles are very hot. The whole thing is moving very quickly. You can't outrun it. 60 miles an hour down the slope of the volcano. Gravity pulls it down as well and increases the speed. And basically throw out a large eruption column, and then all that starts to fall down too. So again, think of what happened at Pompeii, Mount Vesuvius. So these folks, they tried to get to the shore and they were hiding in caves, I guess waiting for boats to come and get them, and the gases overtook them and they suffocated before they were covered in the hot ash. So, you know, that's a major hazard. All right, so if Mount Kilimanjaro decided to erupt, it would create a lahar. The ash, it would cool a little bit, but it would melt that water, and the ash and the water would come barreling down the volcano. And again, you can't outrun it. It flows down the volcano, flows into streams, and sets like concrete when it cools down. Mount St. Helens created a few lahars around its summit or going down. Yeah, so on the left there's a stream, and it took that bridge out easily. You know, it just goes in and cools and really sets. Other hazards that can happen: a volcano eruption, a volcanic eruption, a large one in the ocean, can cause a tsunami to the coast that's nearby. Volcanic ash is not good for airplane engines. If you fly through an ash cloud, that ash will get into the engine, which is pretty hot, and ash will bond to the engine and the propeller and seize the engine up. That's why in 2010, Ayafayaco, I think I said that right, Ayafayaco, when that erupted, you know, that's why they stopped all air travel over Europe. There was a lot of material that erupted from that volcano. Volcanic gases, there's not much sulfur dioxide and, you know, less carbon dioxide than water, but that can still be poisonous to plants, animals, and everything. When one of Iceland's volcanoes erupted, 1780s, I want to say, well, Benjamin Franklin was alive, and he was in Paris at the time, and he took note of the yellow cloud, the dry yellow cloud that covered France at the time and half of Europe. It was sulfur dioxide emitted into the atmosphere. It bonds with water, turns into sulfuric acid. So it chemical burned Iceland and south of there. Anything that, all of the crops that died and people breathing it in, was basically a chemical burn. So on the right, here is a drawing of a large pyroclastic eruption. The wind can also take some of the ash. It goes high enough into the atmosphere, the wind will blow it whichever direction it's blowing in. So if you're over here on the right-hand side somewhere, a couple hundred miles away, you won't have nearly as much ash hit you as it's blowing over there. Any questions so far? Am I going too fast? Nope. All right. Volcanic eruptions can affect not just local weather, but climate over time. Some volcanic eruptions in the far past have just erupted for years and years, hundreds of years in some cases. That would definitely emit a lot of carbon dioxide into the atmosphere and change the climate. In fact, there's one eruption that was contributed to the Permian mass extinction, they believe. So, oh yeah, the 1783 Laki eruption, that's the one that Benjamin Franklin saw in Paris. In that case, the ash material released stayed in the atmosphere long enough to reflect sunlight and caused the temperature near the ground surface to cool. That eruption brought temperatures in New England a lot lower than usual, or for longer. Mount Tambora in 1815, this was another large pyroclastic flow. That year without the summer refers to the east coast of the US. It was so cold the crops failed here from an eruption in the Philippines. And again, that El Chichon eruption produced a lot of sulfur dioxide and again, sulfuric acid. Okay, calderas greater than 1 kilometer in diameter. Crater lake form after an eruption, and then they're filled with rainwater and form a lake. Hawaiian calderas are collapsing slowly at the summit, and basically because the magma is moving back down into the crust below the volcano. For whatever reason it does that, we still don't quite know. Maybe it moves to another place through some kind of tunnel or something. So then that caldera will collapse along the edges. And then Yellowstone was a horrible, very bad eruption. Lots of silica-rich pyroclastic material. The beds of ash and pumice and other stuff in Yellowstone are a little bit different. Layers as you go older. But basically, Yellowstone has been very, very violent eruption about every 600,000 years. So here's Crater Lake, and basically after the eruption, also whatever doesn't erupt flows back down into the magma chamber and then goes back down towards the mantle. Not entirely sure why, but, and you get an island form there. Here's Hawaii. So that's a lava lake. So that circular feature is this right here. And you can actually, not just from historical records, but you can go in there and date the layers to the year that they actually occurred in. So that's the crater that erupted back in 1982, 1971. Oh yeah, so here's Yellowstone. So see how large that caldera is relative to the size of the park. Compared to the eruption of Mount St. Helens in 1980, you can see how far that material was thrown. So that was a very large amount of material. So this ash bed 2 million years ago, MYA means million years ago, covered most of the West there. Then the next oldest, 1.3 million years, covered that much, and then 600,000 years or 0.64 million years ago, it covered that much of the surface. Now, not incredibly thick, but that's how far it was thrown. And they say we're overdue statistically for another eruption. But scientists are constantly watching these types of volcanoes, and in Italy they have their own volcano watch group to try to warn people as quickly as possible to get out of the way of any eruptions. Yeah, so Yellowstone, caldera, a bunch of stuff erupted, but some of it still stayed in the magma chamber, and then this whole bit in the middle of the caldera just dropped down. And maybe there's a couple more lava flows in here, but the main eruption was that stuff there. Okay. Fissure eruptions, that's what I said first, where a fissure can be a crack, a long crack, and then the lava comes out in a sheet-like form. This creates a large expanse of lava called an igneous province or a basalt plateau. And these are called flood basalts. They literally flood the area. The Columbian Plateau in Oregon and Washington is one such place, and the Deccan Traps in Siberia, I think it's Siberia, are another place. That's the one that erupted for hundreds of years and put out a lot of material. So you can see, so here's a fissure, and then here's the lava moving downhill. And this is from that Columbia River basalt. So you can definitely see the difference between that black rock and the rock around it. And this basalt flow is so old that right here, this river cut through all of those lava flows, cut through that large basalt province. So whenever you see a river, like here, like the Grand Canyon, those rocks were laid down first, lithified, and sometime later, water came through. Water can be very powerful and do a lot of work, and it cut down right through all that rock and created this canyon, or the Grand Canyon. So this basalt just started to flow out and just went right down this river here towards the Pacific Ocean. Here's Mount St. Helens, and after that eruption, you can see it blew out that one side of the volcano. Maybe a little bit of lava is still trying to come up. It's like a last gasp, and it forms what's called this lava dome. So that material just didn't get erupted, and it's just starting to cool right there. And that is something to watch for, to see if maybe another eruption is imminent. Okay, if you've never been to New Mexico, go to Shiprock. Actually, also look at it on Google Earth. It's hard to get to the road to see it from the road view on Google Earth, but this sucker is huge. You cannot get on the property. It belongs to Native Americans. There is a road that goes through that they allow people to drive on, but you are not allowed to step off that road. We were pretty far away from it, but man, it was awe-inspiring. This picture does not do it justice. So this is a volcanic neck. This is magma that solidified inside the conduit of this volcano, this extinct volcano. Then over time, all the material around it eroded away. A pipe is another type of conduit that is smaller in diameter usually, and it comes from very deep in the earth. The rock it contains that crystallizes in it is called kimberlite. That's where diamonds are usually found, in that type of rock. Okay. Volcanoes usually occur where two continental plates are coming together, also called convergent plate boundaries. Most of the time, around the Pacific plate, around the edge of the Pacific plate, you've got the Pacific plate subducting under all those other plates, South America, Alaska, Japan. So here we have a subduction zone. One plate, the ocean plate, is more dense, so it's going to want to go underneath the less dense continental rock. So it starts to subduct. As the plate subducts, that rock starts to partially melt. That's lighter, more buoyant. It moves to the surface and creates volcanoes. And the line of volcanoes is called the volcanic arc. These eruptions are usually very explosive and pyroclastic type along the Pacific plate here. So the Aleutian Islands are created by volcanoes. The Pacific plate is generally moving to the northwest. Here is an ocean ridge that separates this plate from this plate. So it's not really the Pacific plate subducting under South America. It's not Juan de Fuca. I can't think of it now. It's this plate is subducting under South America. So the oceanic plates are diverging or pulling apart. And then when, especially along the edge of the Pacific, they are subducting under continental land masses. Here's Juan de Fuca. It's off the coast of Washington and Oregon. That is the remnants of a larger plate that has since mostly already subducted under the North American continent, and a piece of it is still kind of there. You can, when we talk later about sensing into the ground using seismic to remote sense, they can actually see, kind of rough, but they can actually see part of the plate still under North America. So it hasn't detached, hasn't completely melted. When you see a line like this, black line with triangles, the triangles are pointing in the direction that the ocean plate is subducting. So this is the edge right here that's subducting under North America. So this piece of ocean is part of North America, North American plate. And you see all these mountains here: Mount Baker, Rainier, St. Helens, Crater Lake, Lassen. Those are all part of the volcanic arc. This is a great diagram here at the bottom. You've got the plate subducting. You're going to have a trench or subduction zone. The plate gets deep enough, water's driven off, it melts, buoys up, forms volcanoes. This is why the volcanoes are so far away from where the plate is actually subducting, because it takes a while for it to get down. So that distance is how far it has to go before it starts to melt. So you're going to have volcanoes off, definitely not on top of the subduction zone. Divergent boundaries, which I mentioned, so those are like the mid-ocean ridge. They're pulling apart, they're diverging. Most of the magma is from these areas in the oceans. Most of these areas are going to be in the oceans. Lots of fluid basalt lava flows that cover the ocean away from the ridge. And you can have volcanoes that form in the middle of a plate. That's what Hawaii is. So these are called, Marie, these are called hot spots, and they're formed when a mantle plume, a large blob of mantle material, comes towards the surface, breaks through a weak spot in the crust, and that's what forms those volcanoes. So like I said, Hawaii's in the middle of the ocean plate. Galapagos, Yellowstone is another one. Here are a lot of the main flood basalt layers that we can see. So, and they're all been dated pretty much. So, oh yeah, Siberian traps. I keep thinking Deccan is in India. Siberian traps, that's the one that erupted for so many years and contributed to the Permian mass extinction through climate change. Let's see. So right now in Eastern Africa is rifting. So here's a continental rift. And that's what this flood basalt is here. That's why this is here, because you've got the main African continent moving to the west and this part of the continent moving to the east. Mantle plumes, super plumes. This is how Hawaii forms, and a lot of other volcanoes. The tectonic plates are constantly in motion, different rates, but if you get a mantle plume rising up, it breaks through a weak spot in the crust and the plate moves over it, and you're going to get, instead of one volcano, since the plate's moving, you're going to get a series of flood basalts, of fissure eruptions, and then you get a large basaltic province. And you might get some volcanoes later, depending on how active the magma is. But that initial one is going to be a large flood basalt. That's kind of neat. There's so many different things on the planet, and they're all created a little bit differently. So we monitor volcanoes to try to see how hazardous they might be to people. And earthquakes go along with volcanoes. A volcanic eruption can start or be preceded by earthquakes. As the magma moves towards the surface, it's going to crack and move that crust, so it's going to shake it around and cause earthquakes. And the amount of composition of gases is monitored in a lot of volcanoes. The change might indicate that a volcano is ready to erupt. Now we've got GPS and remote sensing. We can go out to a place that's really hard to get to or dangerous to be at, put our GPS device there, and there's a monitor sensor in here, and there's a data logger. You go back once a year, get your data logger, download your data, and you can see if that ground is rising or sinking. And definitely this uses your GPS, your elevation measurements that are very, very precise. Also, you can leave maybe a sensor in some places, but I would just, I don't think they do that. I think they go and take measurements every so often. So a dormant volcano is when it's resting, and then active is when it starts to emit different gases and raise or lower the land around it. Okay. All right. Does anybody have any questions? Nope. Okay. Well, I am going to go ahead and talk about maps a little bit. So.
Sorry, I was laughing. Sorry, never mind. No, different trigger. Sorry
No,
about
you're
that.
fine. You're fine. You're fine.
I was totally paying attention, just that you connected to a different memory from the past that made me laugh. I'm sorry, I thought it was muted.
No, that happened. I get that. I totally get that. Okay. All right. If you want to stay, that's fine. I'll talk about maps if you want to get going. That's fine too. Okay. I'm going to also pull up okay. I am going to pull up something I think is pretty cool. So I've told you that I've worked at the Kentucky Geological Survey for a while, and I helped with one piece, a small piece of their digital map. As far as I know, at least back 10 years ago, Kentucky's the only state that had an interactive map service for free for anyone who wanted to use it. What they did was they scanned all the maps they had. Let me back up a little bit. They've changed it, so I want to. I don't like how they've changed it because I don't know how to use it very well. Here we go. Okay, I'm going to go ahead and share. Move this over here. All right, so if you go to kgsuky.edu and find the Geologic Map Service, actually it comes up like that. You're like, what the heck is that? This is a geologic map of the state. If you zoom in, all these black lines are fault lines, by the way. You can roll your screen, roll your mouse, and zoom in, and we're going to look at a couple of these in class. And it's slow. Let me find Georgetown. Here's Georgetown. So we're going to actually look at this particular map in class. So here's Georgetown. There's the bypass. First, I'm going to, if you come to menu and go to layers, there's a lot of different things you can see here. What I want to do is turn on they have changed this. This is a different GIS server, and I never liked it. I don't like it. Here it is. Okay. You can turn on the topo series and turn off the geology. Don't worry, I'm not going to quiz you on this. This is okay. Zoom in, zoom in. Oh, jeez. All right, I'm going to try to make this a little easier. There's a link to this in Canvas, Geologic Maps, a Citizen's Guide. So here is a topographic map. It shows a city, the roads, here's the city limits, streams, anything green would be vegetation. All these brown squiggly lines are contour lines. They show elevation. These older maps, these older paper maps were created by hand, people going out with surveying equipment and getting elevations relative to sea level. Yeah. Where is, I've got something else that I can't. Oh, where is it? No, that's not what I want. I'm sorry. My computer's giving me fits. I had the map of Georgetown here somewhere. And I can't remember where I put it. Okay. Here we go. I found it. What am I doing? I don't know what I'm doing. Okay. Like I said, I don't know what I'm doing. Okay, here we go. You're going to see a map just like this, and I'm going to show you an older version. So this is the Georgetown quadrangle, it's called. This is a topographic map. The whole US and probably all of North America is mapped like this. I'm going to zoom in a little. This is the newer version, which looks a little bit different. And I know the folks that created this new version, and they don't play very nice. Yeah, long, bitter story. Basically, these brown lines are contour lines, and they represent elevation. If you think about, if you remember those collapsible cups, how they were different sections of plastic, and when you opened it up, it made a cup. When you flatten it down, you have different rings of plastic, right? Different sizes. That's the same thing. That's taking a 3D object and collapsing it down to put on a piece of paper. The Earth is spherical, So it's a little difficult to just, you know, slap it on a piece of paper and it be accurate. So there's a lot of math, I should say math, that helps to take that into account. So here we go. So here's all the roads. Anything blue is going to be water. And I am going to scroll down here a little bit where it's a little easier to see. So you can see some of these contour lines are marked and labeled. So like this one over here says 900. I know it's hard to see. Let me try to zoom in a little more. There we go. So that's 900 and that's 900. These are both 900 feet above sea level. Water is going to be a low point. So if you're walking on here, this is the top of a hill, such that it might be top of a hill. If you walk towards the water, you are going downhill. You can see this contour line is marked 850. So you are definitely walking downhill. When you get to water and you cross the stream, you're going to go uphill again. They don't mark and label every contour line because the map would be too messy. So here it's every 50 feet. So if that's 850, you can follow it along. And every point on this line is at 850 feet above sea level. So if we start going uphill, that one's 860, that one's 870, that one's 880, that one's 890, and then 900. Okay, so what we're doing is taking a hill and collapsing it, putting it on a piece of paper. All right, I'll show you geologic maps another time. So, what else was I gonna? Y'all still with me? When you have the, oh, cool. When you have the maps in front of you, you should be able to see this a lot easier. I'll put a link to that in Canvas, so y'all can just take a look at that. But on the KGS website, if you search in the publications, you can pull up any map from across the state. They are called quadrangles because they are rectangular, not quite a square. And we'll go over, you know, those dimensions during lab. Okay. So how to create contours. Okay, share my screen. All right, so this is an example of the exercise in your book. Each dot is an elevation. Somebody went out there and stood there with either a laser and a stadia rod and measured the elevation of each of these points. I had to do this for class, and we had to use essentially what was a telescope or something like a gun sight on a stable tripod, and then we had a partner over yonder, and we had to they had a stick and it had measurements in inches on it, so we had to actually measure the difference in elevation from one point to another, and that's just part of the process. But let's that was a lot of fun, actually. So we'll go a little bit easier here. This is a stream. The blue thing's a stream, and each of these numbers is in feet above sea level. Okay, so I'm going to try to get a, well, I'll do a marker and I'll do red. So what you do is, yeah, they're not all even numbers, right? So here's 2, there's 12. You can start where you've got higher numbers, or probably easier to start where you have lower numbers. Pretend your stream is 0 feet above sea level. That's easy enough to do. So we're starting to go uphill a little. Here's 2, here's 5. We're going to create 10-foot contour lines. So that is a height of 10 feet. Okay. Each contour line will be 10 feet in height apart. So you look for 10 and anything in between 10. So here's a 10. Well, here's a 15 and a 7. So you eyeball it. This doesn't have to be perfect. So where about would 10 be? So there's 10. So where about would 10 be? Well, maybe there. Well, here's 12 and 2, so maybe 10 will be there. 12 and 16 doesn't have a 10 in it. So your first contour line at 10 feet will look something like that. Let's go to, let's go to 20 feet. You can do whatever interval is easy. Less cluttered map is a good map. The less clutter you have is good. Some of these contractors send me, you should have seen the one I saw today. I couldn't believe it, that I have to look at and deal with. You think they know how to make a map by now. Sorry. So, well, here's 20. Here's a 20 right here. Are there any other 20s? Well, over here, but think about it. There's a 26 here, and 25, and then you're going back downhill, 22 and 25. So you don't count those with this one, okay? You just go from the point you're looking at to the points closest to it, okay? So 20 and 16, so that's going to be your 20. Here we've got 22 and 16, so 20 will be maybe about here. 25 and 15, that'll be halfway. 24 and 15, yeah, about there. So you can go off the paper, that's fine. And it'll look something like that. It's not perfect, that's okay. So you notice that each contour line goes off the page. That's okay. They don't have to connect all on the same page. You can draw it off the page. That's what happens in most maps. Now, if it's a really small hill, so just over here, for example, if you've got a small one like that compared to these over here, that's a very small hill and the contour line can connect. But someplace like this, they're not going to connect. So let's do, I'll put some others in here. So let's do 25 just because I got a little 25 crazy here. So here's a 25, here's a 25, here's a 25, 25, 26, 22, 26, so that'll be about here. 24, 26, that'll be in the middle. And again, you're going to ignore these 20s for right now, and your 25 will look something like that. So why did I put these 20s here? I'm going to go yellow. So we're going uphill, here's 30. Here we're going downhill. So what you can do is connect all the 20s over here you've got. So this will be going back downhill. If it's a sinkhole, like in Kentucky, what they'll look like is they'll have these little marks pointing inward to help indicate you're going downhill into a sinkhole. All right, so let's do 30. So this is 25, and that's 20, and it's hard to write like this. That's okay, and that's 10. You know what I mean? And so for 30, well, here's 30, 27, 26. Nope, 30 will be somewhere over here. 34 and 29, so 30 will be like here. And there's your 30 right there. And that's how you create contours. And you don't have to worry about these in here. So basically you're walking uphill from the stream. Here it gets a little less steep where you have two contour lines far apart like this. It's more flat. When you have contour lines that are closer together, that whole area is steeper more of a hill. Okay, I'm going to stop sharing. Does that help? I hope. I mean, I'm not being critical. I'm hoping that helps. Cool. And then there's another video just like that on Canvas. And drawing a cross section, why don't I fix up another demonstration for Thursday for that?
That'd be good.
Sounds good. All right. So any other questions? If you're stuck on something with the maps, either let me know. We can have a Zoom meeting. We can talk after lab on Wednesday. You know, however you'd like to do that.
Awesome.
Awesome.
Appreciate it.
You're welcome. Have a good night. Everybody stay safe.
You too.